The final topic for Chapter 10 is power. And power is the rate at which energy is transformed from one form into another. Remember that energy is only useful to us humans when we do that, when we transform it from one form into another. For example, right now, here today, I'm teaching a physics lecture, and I'm using chemical energy in my food in order to do that. I'm transforming chemical energy into sound energy, and some thermal energy, I'm getting a little warm, and some kinetic energy. Woo, okay, so, the lights that are here in my light box that I built around my chalkboard, right? These lights are converting energy from electrical energy into light energy, and a little bit of thermal energy also. So, again, energy is only useful to us when we convert it from one form into another. The rate at which that happens is power. And so our units for power are a joule per second, or a watt. 1 watt is 1 joule per second. So take a 100 watt light bulb. That 100 watt light bulb is transforming 100 joules of energy every second. 100 joules of energy from electrical energy into thermal and light energy every single second. Again, power is a rate of energy transformation. And so we can think about that either as an energy transformation right here within the system, but we could also think of it as the rate at which energy is added to or taken out of a system, which is sort of how this equation ends up working out, right? So these two equations are nearly identical. They're almost interchangeable. But this would be the rate at which energy is transforming within a system, and this is the rate at which we are moving energy into or out of the system. We can kind of rearrange these just a little bit, and we can say that for a constant force applied at a constant velocity, we can write that power is force times velocity. So if you take the force and you multiply it by the velocity, that also gets you the power. Here we see two cars. We see a Volkswagen Beetle and this fast race car. These might have about the same mass, and they can certainly both get going 60 miles per hour. But which one takes longer to do that? Well, almost certainly the Volkswagen Beetle takes longer to do it. So if they have the same mass, and they both reach the same final velocity, then that means they have the same final kinetic energy. But we can easily imagine that it would take longer for the Volkswagen Beetle to get there than it would for the race car. This means that they produce different amounts of power. And we can imagine that this car definitely produces the most power, the race car does. And to think about why that is, well, what power are we creating? What energy transformation is happening here? Well, we're converting energy from chemical energy stored in the gas tank to kinetic energy of the moving car. And the race car can do that faster. Why? Well, it has a bigger engine. That bigger engine is just able to take in more gasoline, and so it is just able to convert that chemical energy in the gasoline into kinetic energy much faster. Again, more power because it is able to transform energy faster. Power is the rate of energy transformation. Let's do a real quick example. Let's imagine that an elevator weighing 3,000 newtons ascends at a constant speed of 3 meters per second. How much power must the motor supply to do this? Well, let's do a real quick force problem so that we can approach it from a force times velocity perspective. For the elevator, we've got some tension in the cable and we've got some weight. We know that the sum of the forces in the y direction equals mass times acceleration. I suppose I should tell you that what I mean by the y direction is no reason to mess with our coordinate system here. Since I told you it's a constant speed, the acceleration is 0. This tells me that t minus w equals 0, or that t equals w, which is 3,000 newtons. Now, this tension, right, the tension is created by the motor, basically, right? If our motor quit working or slipped a gear, then we would have no tension, right? And so it is indeed the tension that the motor is supplying, right? And so if we wanted to think about the power here, we'd have force times velocity. So we have our tension of 3,000 newtons, and we have our velocity, 3 meters per second, and that gives us a power of 9,000 watts. Okay, 9,000 watts. Again, 9,000 joules per second. Well, electrical energy goes into the motor, and then that motor is creating... Well, we're not changing the kinetic energy of the elevator, so it's not creating kinetic energy. What energy is it creating? Gravitational potential energy. So here we see that the motor is supplying 9,000 watts of power. So that means that it is creating 9,000 joules of potential energy every second. Where did that potential energy come from? It came from electrical energy. Now, there's something else happening here too, and that is for every 1 joule of potential energy, this motor is creating at least 3 joules of thermal energy. And so here we're talking about efficiency, which is the big topic for chapter 11. So in this case, the output power is 9,000 watts. The useful output power is 9,000 watts. But in any process, when we're converting energy from one form into another, unless that process is reversible, thermal energy is always created. And that's the topic for chapter 11.